Here are the notes for section 7.5. The title is Binomial and Geometric. These are two types of discrete distributions. Discrete distributions often appear in a table, and instead of having numbers that are filled in by observation, they're filled in by mathematical formulas, so we can predict what the probabilities are going to be based on formulas. The good news is that we're not going to be using these formulas too much. The calculator will be doing most of the heavy lifting. Our job is to figure out when a situation is binomial or geometric or neither. So the requirements for binomial are you have to have a fixed number of trials. There are only two outcomes, and they're usually labeled success and failure. The trials are independent, and the probability of success does not change. And a classic example of a binomial situation would be somebody shooting free throws. So let's say we take batches of free throws 5 at a time. Your fixed number of trials is 5 free throws. Every free throw is either a make or a miss. We're thinking that just because you miss one doesn't mean you're going to miss the next one unless there's an injury or something, but let's assume there's no injury. And then we're assuming that a shooter has some sort of natural innate free throw shooting ability, so the probability that he or she makes the free throw is going to be the same for every trial and it doesn't change. So if you satisfy these 4 conditions, you get to use this formula for predicting how many X free throws out of your fixed number of trials, 5, would be successful. And then you're going to learn how to use this formula in the examples coming up on the next screen. One thing I'll tell you is that if you haven't seen this notation before, this is combinatorics notation. Out of n things, how many ways can I arrange or choose X? Out of 5 free throws, how many can I make 2? In other words, make, miss, 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 or make, miss, miss, etc., etc. This is inside your calculator. If you press the math button, probability, and go down to NCR, this is one of the few commands that requires both an input before and after the actual calculator command. And again, you'll see that in class. Like all discrete distributions, this table will have a mean and a standard deviation. The formula for the mean of a binomial, you don't have to actually calculate all the values. You can jump straight to n times pi is the formula for the mean, and you can jump straight to this formula for the standard deviation. So let's say there's a free throw shooter let's say there's a basketball player that's going to be taking 10 free throws, and she makes on average 70% of her free throws. The mean is pretty much a common sense situation. If I have 10 free throws and I'm a 70% free throw shooter, 10 times 0.7, we're going to expect her to make 7 of the 10 free throws on average. Geometric is very similar, except it's missing one of the requirements. There are 3 requirements. The first is that it's the same as all these, except you don't have a fixed number of trials. Okay, so if you take these 4 and eliminate the possibility of a fixed number of trials, you have geometric. And what makes geometric unique is that you're going to stop as soon as you hit your first success. So again, talking about free throws, a geometric situation would be how many free throws would someone need to shoot before he or she makes her first free throw. So that's a geometric situation. The formula here, again, we're not going to use that a whole lot. We use our calculator, or actually geometric a lot of time. Just you can figure out using common sense. You could put all of your values in a table, but this table could go up forever. In binomial, if I say I'm going to be shooting 5 or 10 free throws, I know that my n is going to be 5 or 10, and I can make 0 or 1 or 2 or 3 of that fixed number of trials. In geometric, in theory, you could keep shooting forever and keep missing and really not ever make a final free throw. But when you do make a free throw, you're going to stop and end your table there. The mean, or the expected number of free throws, is just the reciprocal of the number of trials that you're going to have. And then the standard deviation is a formula that we don't need to worry about a whole lot. I just realized that there's a typo. This mean formula doesn't make much sense. I just got done saying that there's not a fixed number of trials, so there is no n, so the mean can't be the reciprocal of n. The mean is supposed to be the reciprocal of the probability of success. So that's the formula for the mean. Okay, the next 2 slides are going to walk through an example of a binomial on this one and then a geometric on the second one. So 12% of manufactured mufflers are defective and 10 mufflers are selected at random. So our fixed number of trials is 10 mufflers. The probability of getting a defective muffler, we're going to call that success, even though you wouldn't generally associate a defective muffler as being successful. But the probability of success is 0.12, and now we're going to answer these questions. Calculate the probability that of your 10 mufflers, none are defective. So by hand means I'm going to take n is 10, x is 0, the probability of success, a defective muffler, is 0.12, and the complement for the probability of success is 1 minus 0.12, which is 0.88. So breaking this formula down, out of 10 mufflers, how many ways can we arrange 0 defective? Well, there's only one way. 10, choose 0 is going to be 1 from your calculator, or if you think about it, write the word non-defective 10 times in a row, and that's the only way you can arrange having 10 mufflers selected and 0 non-defectives. If defective is a probability of 0.12, then 0 of my mufflers are going to have a 12% probability, and 10 of my mufflers are going to have the non-defective 88% probability. So multiply all these together, we get the probability in my selection of 10 that I get 0 defective mufflers is 0.2785. Again, that's a little bit of work, so we're going to use our calculator to find the rest. In the table, and you'll see how to use the calculator in class, I took 0.2785 and rounded it to 0.28, and then I used my calculator to figure out the rest of these. The command that you should write down in your notes is second vars binomial PDF, and then the 3 arguments are n, p, and x. And instead of typing in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into my calculator, I actually stored these values in a list and told my calculator figure out the binomial probability for 10 fixed trials. Probability of success is 0.12, and the outcomes, or the number of defective mufflers I'm looking for, are contained in this list, and you'll get this list of numbers. You'll see that in class. Once you have the table set up, answering the questions is pretty straightforward. What's the probability that x is less than 2 or fewer defectives? I'm going to go to 2 or fewer and add those 3 amounts up, and I get 0.891. Since answering a question like something or fewer is fairly common, there is a shortcut for that as well in your calculator. Instead of calculating binomial PDF for probability, we could do CDF, which is cumulative probability. If I say 10 for a fixed number of trials, 0.12 for my probability of defective, and 2 with a CDF command, that means cumulative 2, 1, and 0 added together, this cell, and this cell equals 0.891. Probability that more than 2 are defective, probability x greater than 2, that's the complement. Well, that's actually asking for 3 all the way up through 10. That's the complement of 2 or fewer. So if the entire table has to equal 1, to answer greater than 2, which is 3 through 10, I could just do 1 minus 2, 1, and 0. So probability 1 minus the probability of x is less than or equal to 2. I got x is less than or equal to 2 up here in this 0.891, so it's just the complement of the previous question. And then finally, find the mean and standard deviation. Plugging into the formula, mean is n times pi. So on average, in 10 mufflers, I'm going to expect about 1.2 mufflers to be defective. Again, means can be decimals, even if 0.2 of a muffler doesn't make much sense. And the measure of spread helps us figure out how much variability there is around this mean. Plugging into that formula and taking the square root, the variability, the typical deviation from the mean of 1.2 is about 1.03 mufflers. So the geometric example is this. Suppose a couple plan to have children until a boy is born. Use probability of a boy equals 0.5126. So this word highlighted here is an indicator of why this is geometric and not binomial. The couple is going to continue to have children until success, having the boy that they're looking for, occurs. Find the first 2 values in the distribution by hand. Well, if you get a boy first time around, you're going to stop, so 0.5126. If you need x equals 2, then your first would be a girl and your second would be a boy. Probability of girl is 1 minus 0.5126 times probability of boy 0.5126, that one there. So without that fancy geometric formula, it's kind of just common sense. You take and continue to use the complement until you wind up with your single success, which ends the process. Next 2 values in the distribution using a calculator. Calculator, just like binomial, has a geometric command. Geometric probability, so geometric PDF. We don't have a fixed number of trials, so the first argument, the n, disappears. We just have the probability of success and x, the number that we're looking for. So what are the chances that this couple has to have 3 children before they obtain their boy? 0.51263, and the geometric PDF command is this. What's the probability they have to have 4 children until a boy is born? 0.51264 leaves you with 0.0594. Mean of the distribution, again, the correct formula is here, the reciprocal of the probability of success. So on average, they're getting close to 2 children before they're going to have a boy. It takes close to 2 kids before a boy is expected. And then to answer these, the probability of x is less than 2. If you set up your table, x is less than 2 was only this case here, so 0.5126. Okay. Probability that x is less than or equal to 2, we're going to use the geometric CDF cumulative. So single command 0.5126, 2 in the CDF command for geometric gives us this, which would be the same thing as these first two cells added together. And the probability that the number of children is greater than or equal to 4. Again, this can go on forever, so it's really impossible for us to calculate this by adding up 4, 5, 6, 7, 8, 9, 10. So we're going to figure out the complement of this situation. The complement of 4 or more is 3 or fewer. 3, 2, 1. Again, geometric CDF with a 3 here. Complement of that 1 minus gives 0.1158. Okay, so that's a brief overview of binomial and geometric. You'll learn calculator commands and more practice in class.